I'm Gavin Ferris. I'm the pro bono CEO and co-founder of a company called lowRISC CIC. I'm here to talk really about the role of collaborative engineering more generally, really, because it's kind of a bit of a new thing in silicon. It's been around for a long time in software, obviously. And specifically, the role we think it can play in accelerating hardware and memory safety technologies, specifically Cherry. So that's kind of the background to this talk. So a little bit of background just briefly about lowRISC. We're just over 10 years old now. We spun out of the University of Cambridge Computer Lab, as it was then, Department of Computer Science and Technology now. We're a non-profit, so we're a CIC, a community interest company, not a charity. We can run profits on local projects, but then we can't divest them with no shareholders, so we have to plow them back into education or other projects for the benefit of the community. And our goal, our overall goal, is to help make open source silicon designs a commercial reality, right? And obviously benefit with that the academic community and so on. So that's kind of what we're about. We've been growing over time. We're now about 30 people overall. We're based in Cambridge, UK primarily, but we have a satellite office in Zurich because we're very tightly connected with ETH over there. And we have a company that we own in Canada that makes circuit boards, right? Because that's a necessary thing that we need. We're founding members of the RISC-V Foundation, the Open ISA, and also founders of the Cherry Alliance. And in fact, the Cherry Alliance legals was largely seeded off the legals that had been through many large companies' legal departments with lowRISC and OpenTitan, so that we weren't starting this from a cold start and finding that the first US company that looked at them would say no way, right? So that's kind of where we're at. And I want to talk a little bit today then about what we've been doing and what collaborative engineering has really achieved so far. So first of all, at a very high level, right, because this kind of stuff can get quite geeky, what is collaborative engineering? Well, traditionally, if you've got something that's expensive, really expensive to do, like hardware, and it costs tens to hundreds of millions of dollars to make a chip, you will be locked into an ecosystem, to sort of pick that up, where only very large players, big cos, if you like, can play. And one of the things a big co will do, sometimes deliberately, sometimes accidentally, is try and own the entire stack, right? They'll create a moat by owning everything. It's all too complicated, it's all interconnected, only we're big enough to make it happen. That means lots of money, and it means a few players, but it means the system is inherently not anti-fragile. It's not a diverse ecosystem. They're not really competitive, and if one of those large companies decides to not pursue a technology, for example, you can find that the magic disappears. So how do you get around that? Well, the goal is really, or the point of collaborative engineering is to say, look, only a little bit really of what you do in any engineering practice is truly a USP, unique, or something that differentiates your company. Most of it's foundational. You need it, but it's kind of pretty much something that everybody sort of knows how it works. There's nothing unique to your company differentiating. The idea, which of course is commonplace in software design, is to say, look, let's take all the shared components, put them into a commons, obviously manage that in some way. It doesn't manage itself. Tragedy of the commons is a real thing. But put it into a commons, and then that allows smaller companies to act like virtual big companies because they can create the same artifacts, the same results, by only or primarily focusing on the things that differentiate them, their USPs. So this is not saying we want open source because we've got some sort of communitarian ideals. It's saying it just makes more sense not to keep reinventing wheels and to focus on the stuff that is truly differentiating. And that's been a way of working in open source software for some time, but not in hardware, right? And so our goal is really to make it more like that for hardware. Yeah? The advantage of doing that, if you can do it, of course, it removes or reduces the barriers to innovation because there are lots of more SMEs than there are and startups than large companies. And by the way, we're not excluding large companies. Large companies are absolutely willing to play in the commons as well. We obviously reduce duplicated effort. We're boosting efficiency, to actually get stuff done because you're concentrating on the new things, improving standards and skills, and also supporting research because with that open commons, if you're a research department, this actually happens quite a lot. So, the model that a lot of people have in their heads is that I'm working at a university, I think of a thing, the research pipeline generates an artifact, we start a little spin-out company, the spin-out company commercializes it, off we go. The problem is in things like chip design, all the innovation is happening inside companies who are loath to allow the academics access to that. And it's hard to improve on the state of the art if you're not party to what it currently is, right? So having a large commons also facilitates a virtuous circle with academia, right? People can take that stuff, improve it, run their tools on it. It's permissively licensed. They don't have to ask you permission. And then you benefit from things that they have generated and can feed into your ecosystem in an ideal world. And it also guarantees long-term access. So if one of these companies decides not to pursue a technology, it can die. If one of these small companies goes away, the commons is still there, right? So there are countless tales of either startups that have gone away and their technology has disappeared with them, or large companies have decided not to pursue a technology and it has also gone away. And having stuff in the open source is a good prevention against that, right? So there are lots of benefits to doing this. But there are also differences, right? So we saw Reid brought up the Cathedral and the Bazaar, the famous treatise in open source software. One of the premises there is release early, release often. Right? And you can't do that with hardware because there's a chip on a board and the board's gone out somewhere and you can't reach out and fix it if it's wrong. So as a result, we have to do a lot more testing in silicon. There's a physical supply chain. There really isn't with software. You can upload bits to the cloud and off you go nowadays. That's not true. There are far fewer engineers who are talented or available or skilled, I should say, in hardware than in software. And the costs of tooling is very high, and mask sets and production and all that stuff. It's just millions and millions. So it's not something you can do on a part-time basis. You really have to have the funds to commit to it, and you have to have the testing to commit to it. You have to have a multi-year program to make it work. So whilst there are things that are similar in software and hardware, there are things that are very different. So really what we came to the conclusion in lowRISC was what we actually had to solve was a business model, an operating model, and a governance model around how you do open source silicon design, as much as the how do you actually physically sit down and write RTL or whatever, right? So we have this thing called the Silicon Commons. We didn't come up with it on our own. It was a collaborative, meta-engineering task in itself with our partners, which I'll talk about in a minute. But this is really how you take the best bits of open source software. So yes, we have RFCs, we have code reviews and all that stuff. But how do you make it work for silicon? How do you make that actual translation? So there are things like how do you do verification, design verification tests before you release the thing? How do you do things like make sure that there really are things like threat models and so on published and so on? How do you do provenance guarantees for hardware and so on, so you don't get large blocks of RTL just dumped in? So these are things that we've been working on, and that Silicon Commons is available. We do training on it. Okay, so first of all, is this a theory? Is this a nice sort of idea? Is this a business school sort of seminar about things that might be, or is it something more than that? Well, it's definitely something more than that. So our primary or flagship project has been OpenTitan, and we've worked on Cherry as well. So OpenTitan isn't Cherry, or at least not yet, but it's interesting because it's collaborative engineering in silicon doing something kind of world first. So it's worth just talking about, I think, for a second. So we've had this partnership with Google and others for over 5 years now, building OpenTitan. So OpenTitan is a root of trust chip, so it's a secure microcontroller. It sits in the target, as you'll see, is one of Google's sort of main product sets, Chromebooks. And it provides secure boot, and once you have booted up your system, it provides a way independent from the main computer CPU and operating system to store secrets and do things with those secrets, right? So credentials. So they're in lots of different devices. People do use them, but what we tried to do here was to take as much as possible of the design stack and make it open. You can't do it all yet because there are things where they're still near the foundry boundary. There are still proprietary things. We didn't try and stop using EDA tools, design tools that were proprietary. We tried to do what we could and make a full open source RTL design test and so on, and publish all of that and publish it Apache 2 license, right? That was the goal, and it succeeded basically. So we have produced from that the world's first commercial grade open source chip, and by commercial grade I mean it has all that test collateral that's associated with it, which is the bulk of the, you see the design on the top, but the bulk of it's the iceberg below, which is all test, which goes into commercial grade. That's actually been done. All of the side channel hardening, the fault injection hardening, all of that stuff that goes into a real system has been done, right? So in a full sense. The chip exists, the engineering sample's back, it's verified. Production is underway now. Production chips will be coming out next year. And that chip is heading into Chromebooks, so it's actually going into a real commercial socket. So that's something that's a world first. I mean, it's great that sort of a UK company has been part of that, sort of bringing that whole group of engineers together. But importantly, it's collaborative. So we actually have the world's most active open silicon project as well. So in terms of, heartbeat on GitHub or whatever, people are actually doing it, using it, interacting with it. It rhymes with the way you do software, but it's not the same. So it proves that it's an existence proof, okay? So when we talk about collaborative engineering for silicon, it can be done, and we think it's really valuable because obviously you want to lower the barriers to entry in terms of getting cherry technologies like that out there, and hardware is the sticking point, right? Getting the languages rewritten and stuff like that, maybe you can use an LLM or something for that, but getting the hardware out there, it's not going to help you with that. You need to actually change it, and the more people who are generating hardware, pardon me, the better. And the smaller the company that can do that, the better, and actually being able to do collaborative engineering is great. So we have here a board, so there's a real open type chip on here, so the silicon actually exists. This is not an FPGA, and you can, of course, it says, boot it, and we can show you in the demo hall outside if you're interested. We show you various things, various demos, but it has an ECB penguin, so it is definitely doing it. Okay, so that's Open Titan, and that's not yet a cherry thing, but it proves that it can be done for silicon. Now, pivoting to cherry, we've also been involved through UKRR DSBD project called Sunburst in producing a development system, a prototyping system that enables people to take Chariot. Talk a little bit more about what Chariot is, but it's essentially the sort of Microsoft thing that you've heard about, which is this low-cost sort of microcontroller implementation of Cherry, so the minimum possible Cherry, right, and be able to run things on it in advance of there being actual silicon, right? So there's not a chip yet, but there will be hopefully soon. Come on to that. And there are two projects out, Sonata and Symphony. So I'll focus on Sonata. So this is what, at a high level, Chariot is. Okay, so Cherry, remember, is this hardware technology. IBEX is the CPU core, which is inside OpenTitan, actually. So IBEX came in as lowRISC from ETH Zurich. We improved it. It's IBEX, now one of the most popular RISC-V 32-bit microcontrollers. Microsoft picked that up, added the Cherry extensions to it, and co-designed an RTOS with it, so Chariot RTOS, so that these two things work together. And that whole system's called Chariot. But that's a core and a bit of software. It's not enough in itself. It's not a complete system. You need a top level to actually make it into something that you could put on a chip or you could put on an FPGA. So that Sonata is developing and designing that top level. And by the way, lowRISC was worked also with Microsoft to help bring that Chariot RTOS, or sorry, not the RTOS, the Chariot RTL to production grade in the same way that we did with the OpenTitan technology. So we have got a board. I mean, one thing I just want to correct, Sonata isn't just a board. We did do an FPGA board. It's here. It's necessary to have a board because you want to have a target that has all the interfaces that you need, that where there's the FPGA on there that has the size and capacity that you need to have. And so we designed a board as part of this. Again, that's open. You can buy it. 100 of them were distributed free as part of the Innovate project. But the schematics are all open. And you can also buy it on Mauser if you want to just go and buy it. You can just do that. And it's got all these different headers and features on there. What is an FPGA board? But the point is that there's a top-level design that you can load the bit stream into the FPGA, which is an implementation of, yes, the Chariot RTOS, or the Chariot core, sorry, the IBEX core, but also all of the surrounding peripheral components, many of which came from OpenTitan. And so there's a board here, and you can again see that outside, and has multiple features and standard Raspberry Pi hat and blinking lights. So it's the non-technical version of Cherry. But it works. Okay, so that's enough about that. But as I said, the important thing to note is that what's in there in the FPGA is a bit stream which includes, yes, this Cherry IBEX core, but all these other pieces as well. So there's USB component, SPI, UARTs, I2C, and PinMux, all the other stuff that you need to surround a core to make it actually into a working standalone design. It's called a top level. A lot of these components, as I say, we've taken from the back catalogue of OpenTitan, which is great, right? They've already been done, they've already been tested. So all that money's been spent designing them and verifying them. Why not reuse them? And we have, okay? So that's Sonata, and that's been very successful, and people have been able to take that and say, oh, I want to add another interface or change it. You can change the RTL, so FPGA, you can do that. Or I'm just interested in running code on it. Just give me the vanilla thing, and I'll just load a code on it, and I'll run it. And it's actually got up to, the whole system is now at version 1.0, which is great. Greg will talk a little bit more about that later. But that's something that we've done, obviously, collaboratively. It's not just been us, it's been working with the whole community as well. And that's been a good success, which is nice. And so, as a result of that, and this is new news as of yesterday, is that UKRI have agreed to extend that project. And that's a top level. It's sitting there in the FPGA. It'd be kind of nice if you could tape it out and actually have a chip like you have on OpenTitan. Well, that's exactly what this extension to the project is going to do. So SCI, SEMI, who include, over here, actually, table out there, and you can go and have a look at their stuff. But Hayden and well, David Chisnell, and a number of other people from the original Microsoft team who worked on this, part of SCI, and they're joining as project partners, have joined as project partners, I should say, in Sonata, and we're working with them to produce this top level. They're going to do all the proprietary parts to that and actually create a 22 nanometer MPW chip. So there will be a chip that comes out of this that implements and instantiates that. You don't have to wait for the chip. You can sort of start playing with the software that could run on the chip on the board right now. So I think that's a really good example of, it's the same thing happening, right? So you look at small companies like SCI that wouldn't be able to do a design from scratch, but they're able to use this because Microsoft open sourced the design, which was based on our IBEX open source design, which was based on ETH's open source design originally. There's a top level because all those other components that are highly verified came from OpenTitan, and we were able to put those together. And so a relatively small team can do a lot, right? And that comes back to that big codes versus virtual big codes thing that I showed at the beginning. That's the point, and it works, right? So a UK company can leverage that to do something that it otherwise could not do. And I think that's highly significant. So, nearly there. Just worth pointing out that one of the things that lowRISC does, as well as all the other stuff, is we are an open source, we're definitely based around collaboration. We want to bring more people into the community. And so we do a lot of training events, and we do a lot of dissemination events. We go to conferences, and we do things like this, right? And also, we were, one of the key founders for, right at the beginning of the Cherry Alliance, because we saw that you needed to have a group, a place where everyone could come together from industry, academia, speak with one voice about this really important technology, and people listen to it and not feel that it's particularly speaking to one ISA, or speaking to one vendor or whatever. So I think then, to sort of finalize this, what I would say is that the takeaways are really that collaborative engineering for hardware works. I mean, there's an existence proof. There's real silicon that's been done with Google, and it's going into real sockets in Chromebooks. The same thing is now happening, right? The same thing is happening, but quicker, because it's able to use some of that, those Lego blocks with Sonata and with SCI in their Iceni range, which will ultimately benefit from a lot of that work. And there will be others, right? There'll be other startups. It's not just that. If you want to take that, this is a great template. This is a great set of digital commons for you to start your company, or for someone you know to start a company, right? So we're facilitating that. We're facilitating that many people participation that is necessary to get take up and to get hardware. Because who knows what the right set of features will be that actually match what the market wants. And then in terms of that commons, what's our role? It doesn't have to be us. It can be a company like us, but we're a non-profit engineering company. And we exist to fill the maintainer of the commons type role, because academia is not incentivized to do that. If you're an academic, you're incentivized primarily by publishing papers. That's the metric. If you're a company, you might want to do a JV with someone, but ultimately you want more stuff for yourself, and that's how capitalism works. I'm not criticizing that. I'm just saying that's what companies do. So if you want, and if you don't maintain it, stuff will then bit rot. Or you get things like the XZ problem, where bad code is injected in because the maintainer is not looking because they're overworked. Or you get the sort of myth of many eyes, like we saw with the OpenSSL issues, where there's a big problem and nobody saw it, but nobody said, well, it's open source, somebody must have looked, and nobody had looked because nobody had been paid to look, right? So you have to have something that's paid for to maintain this properly. You need managed open as opposed to just open, and that comes with the territory because of the cost. And so this is what low-risk role in this ecosystem really is, to come back to the ecosystem. So we manage that open IP, we do project hosting as well. We do training on Silicon Commons. How do you do it? If I'm used to the old style Silicon flows, how do I do it? We do side channel fault injection hardening. We have expertise in certain things like post-quantum, like the Open Titan supports post-quantum signatures, commercial grade DV best practices, and basically supporting the UK semiconductor design and core competencies. And of course, we've worked with non-UK companies, like large companies like Google, Seagate, Western Digital, Winbond, etc. as well. So it's not UK-centric, but I think it has a big value for the UK ecosystem. So that's really the conclusion of the talk. So I've slightly run over, 0. So there you go. Doesn't go negative. Thanks very much. Any questions?